So this section is really going through the messaging, and also there's a large focus on multi-language capabilities that we've been developing across various parts of our tool set. But I thought I'd start this section with two quotes from quite a well-known article from all the way back in 1983, when Fortran was the ascendant language, and Pascal was really sort of moving in to the territory. And although the article's somewhat tongue-in-cheek, it does draw attention to the often sort of fairly narrow outlook among developers and the community that they've landed on the one language, and things tend to get pulled into that one language more than they necessarily should do, as it tends to be overused for its design purpose. But our view is very much different to that. Programming languages are really best viewed as forming a collection of diverse tools. Each one's got its own broad appeal. Each has got their own advantages and disadvantages, both technical and non-technical. But what we want to do is make sure that we can offer the correct language for the correct use case. So to put this into some context, over the years, my own exposure has been around about 30-odd languages. By no means all of them used to the same extent. There's some highlights in there that have been used far more than others, but it just gives a flavor for the kind of exposure that you can expect to see across the landscape over different application use cases. And also, finally, one of my other favorite quotes is from my own son a couple of years ago, when I was introducing him to Scratch, and he happened to be asked in school around that time about what his parents were doing, and he came out and said that my dad works with computers. It's like Scratch, it's just for grown-ups, and that should cut everyone down to size when it comes to comparing languages. So what does all this have to do with the real world? So typical enterprise organization has a mix of teams, varying levels of technical expertise, different use cases, different requirements in terms of fault tolerance, high availability, developmental agility, immediacy of results. And it's completely natural for these diverse areas to gravitate towards different technologies. So a canonical example that we come across repeatedly in this area, in this domain, is quant desks. And they typically want to rapidly prototype different algorithms, preferring languages such as Python for its relative ease of use, tremendous tooling for mathematical and scientific use cases. And that in turn translates to shorter development cycles, allowing the users to keep the focus on the algorithms and the business use cases. So these models in turn will typically draw their input from the core trading stack. And that's typically going to be built for scale, resilience, performance. And so they'll be using low-level C++, Java, or increasingly Rust. So even within a core trading stack itself, it's quite common to see a mix of even these technologies across different components, such as the algo engines, the smart order routers, fixed engines, exchange connectivity, market data feeds, etc., as each pulls on a sort of a different bias between the different languages. And of course, the motivations for preferring one language over another are not just technical. So although this is necessarily something of a generalization, industry stats consistently show that it's both cheaper and easier to build Java development teams with C++ next. Rust is currently something of a slightly distorted outlier because of the current high demand for a relatively small size pool. It also used to be the case that C++ had something of a reputation for much longer development cycles than Java. Larger projects tended to be prone to somewhat spaghettification of code, some really nasty low-level bugs. But this really hasn't been the case for getting on for the best part of 2 decades now. And the per development time to delivery metric across each of these languages is really more or less the same these days. But we appreciate the various motivations for mixing languages and in development stacks. And so that's why we provide Java, C++, Rust, and Python interfaces to Chronicle Q. We've prototyped others, such as Go. And in addition, we support multiple platforms with both x86 and ARM64 versions available for both Linux and macOS. These interfaces are all syntactically similar. So a user that's already familiar with one API can transition more or less seamlessly across to another interface. And in addition, the implementations are fully binary compatible, which is a key point that we maintain across all of the implementations. This allows easy mixing of components using the different APIs. Diverse interfaces provide seamless interoperability, and they help leverage the developer resources most efficiently. It also eases the transitions to new technologies, with Rust being a particular example right now. So on this point, particularly excited to release our Rust implementation for Q earlier this year, back in January, February time. And this was in response, as Peter touched on earlier, to the real dramatic surge in interest that we saw through 2022. Rust had been on the boil for some time, but we really noticed an uptick in 2022. And the rise in popularity of Rust is entirely justified. It's a well-evolved modern language. It's adopted what works well from other languages, trimming out the parts that add unnecessary complexity. The borrow checker brings something genuinely new to the table, and the documentation and packaging system is very nicely and effectively integrated. The result is a highly capable, performant language with some improved safety, which regularly tops lists of most loved languages, as again Peter touched on earlier. And I think Rust has been the top of that list for getting on for 7 years now, with some justification. So the next diagram illustrates the relationships between the current Q implementations at Chronicle. So first, on the left-hand side, we've got the original Java implementation, with the open source core, together with a number of enterprise extensions such as HADR, performance optimizations, encryption, etc. And other implementations of Q, all of the other implementations of Q are enterprise only. So the C++ version is a pure C++ port of Q, and that's implemented from the ground up to prioritize the very lowest latencies and minimize jitter, with native implementation allowing very low level optimizations to maximize performance. In addition, we also make careful use of template metaprogramming techniques to allow a lot more of the functionality to be baked in and optimized at compile time, further reducing the runtime overheads. So as touched on earlier, the C++ implementation is also fully binary compatible with the Java implementation, and supports mixed appenders and tailors in either direction. So you can have appenders in Java, tailors in Python, and everything's working against the same common queue. So for Python and Rust, we've taken the C++ core and wrapped the libraries to expose the Python and Rust APIs respectively. These wrappers are themselves functionally quite deep, and especially in the Rust case, and that's both to minimize the overhead of crossing the .so boundary and also provide a much more natural API for the specific languages. So Java, C++, Rust, and Python are our current full set of Q implementations, and they're fully binary compatible, fully interoperable. We're also seeing some growing interest in Go, and we've put together a small POC for that case. Go is a little bit interesting in the sense that it doesn't have a natural interface to C++, so there's a thin intermediate C bridge that's currently used between Go and the C++ core. There are also a couple of more specific lower level technical challenges with Go, regarding the stack differences between Go and C++ type languages. So that does it somewhat complicates the wrapping, but we're continuing to review the interest in Go and target application use cases before finalizing the decision to support or the approach to supporting Go. And finally, as we've touched on earlier, the native low-level access that's available with C++ allows some pretty specific optimizations which enable us to extract the very best performance. However, some of these techniques, unfortunately, just aren't possible with Java, even in principle. So for some very specialized Java use cases, we're wrapping the C++ implementation behind a JNI interface, which yields net performance gains. So with the benefits of the C++ outweighing the overhead of crossing the JNI boundary. And again, this is very much at the POC stage, but it's just another example which underlines how keen we are to explore all the options and partner with our client base to maximize their performance for each individual use case. Okay, so this slide shows the current multi-language offerings across the Chronicle products. So beyond Q, we have extremely high performance multi-language, multi-reader, multi-writer ring buffer, which we call ring 0. And that's for messaging between components on the same machine, where the extra functionality and capabilities of Q are not required. Some example performance numbers for ring 0 are coming up later, but the benefit with ring 0 is we're able to trim some of the functionality to sort of really pack down the feature set. We're able to unlock tremendous performance, which we'll show in the graphs in a moment. So ring 0 is currently Java and C++. So Rust implementation is likely to follow in the near term. The Map-Kit Data Distributor, the MDD. This is a specialized low latency distribution framework for high frequency data across multiple threads and processes on a single host in cases where messages can be conflated. And this is versus Q, which is persisting every message. And again, the primary application for the MDD is the distribution of live market data across a number of consumer applications. Again, this is currently Java and C++. It would be a very natural and suitable component for Rust addition as well, although there's no current date for this implementation. The matching engine is currently Java only, although we're certainly excited to announce that a 100% pure Rust implementation is nearing completion, and expecting to make that fully production available before the end of this quarter, before the end of the year. For completeness as well, in the context of multi-language components, we also have standalone C++ only components, which include Chronicle Q, which is the performance benchmarking suite, performance tuning suite, which we'll get on to a little bit later on in the webinar. And also the benchmarking suite, which is for profiling whole system and low latency application performance. So these are both self-contained standalone applications rather than libraries. So in this case, there's no particular driver for porting to other languages. So unsurprisingly, outright performance remains a key metric across the industry, and this is another big driver for the multi-language developments as we look to leverage the different tools to maximize performance in each use case. So with the current Q implementations, the performance profiles as shown in the diagram, with Go currently only a POC with some specific language complications as I touched on earlier. At the other end of the scale, we have the C++ implementation, which provides the lowest absolute latencies, together with extremely well-controlled jitter. Python and Rust implementations both directly leverage the same underlying core C++ libraries, so we're going to approach similar performance. For Python, the language crossing overhead is moderate, so we're looking at around about 300 to 400 nanoseconds to cross the SO boundary into and out of C++ from Python. Whereas with Rust, we approach C++ performance very closely indeed. So with Rust, there's really two sources of overhead. The first is the additional runtime checks from the language itself. So Rust does run with slightly higher runtime checks, certainly compared with C++. Not many, but they are there, and they will carry some overhead. So that means that well-written Rust will normally approach, but practically is unlikely to exceed the performance of well-written C++. Then there's also, in our case, where we're wrapping the C++, there's the foreign function interface crossing overhead. But unlike Python, for the Rust C++ case, this is extremely well controlled. So we're looking at around about 25 nanoseconds to move between Rust and C++, which makes it a much more tolerant use case. So Java typically floats somewhere around the Rust and C++ libraries, and will certainly approach the C++ performance across a range of percentiles. The exact relative performance between Java and C++ is somewhat dependent on the specific workload, and is very much dependent on both the quality of the Java code and the capacity of the JVM to on-the-fly optimize code beyond what C++ can achieve at static compilation time. These two often go hand in hand. And this is one of the key differentiators of the Chronicle stack, of course, where we've got a highly optimized Java core. So for completeness as well, it's also noted that JVM does tend to become a little bit more intrusive when it comes to outlier performance. So we generally see consistent divergences begin to appear between Java and C++ at the very highest percentiles. And this is one of the things that Tune is particularly effective at bringing that gap back down into a more manageable range. So the following two plots show some example end-to-end latencies across the stack. So these are 256-byte messages, which is sort of the reason we choose that is it's a fairly typical message size for financial trading application stacks with new order signals, execution reports, for example. So we're pushing these through at 100,000 messages per second, and we do this over 1 million runs. And this is also running on completely off-the-shelf commodity hardware. So this is a Ryzen 7950, which is the latest generation Ryzen's 16 core. And this is also running with Chronicle Q applied. But what we'll see here on the blue plot to start with is the Q performance for C++ and Rust. On the scale of this plot, C++ and Rust pretty much plot on top of each other. And what we'll see is we've got very good baseline end-to-end of around about just over 200 nanoseconds, but also very well controlled. So even out to the 5 nines, we're still under half a microsecond for end-to-end exchange of 256-byte messages on commodity hardware, which is a great baseline performance for Q. Moving on to Ring 0, as we touched on earlier. So Ring 0 trims away some of the additional functionality that to give you a much more sort of leaner but more volatile in the sense that when I say more volatile, it's generally backed by TempFS. That tends to be where we see most of the use cases for Ring 0, but absolutely it can be backed by disk as well. So it is a persistent mechanism as well, but of course it's volatile in the sense that it's a ring buffer, so it's going to overwrite the earlier data. But you do have persistence of the last n messages should there be a failure for any reason. But with this, we're looking at properly low end-to-end latencies. So we're sub 100 nanoseconds. I think if I remember right, the medians are coming in around about 75 nanoseconds for the end-to-end transfer of, again, 256-byte messages across Ring 0, which is pretty close to the limit of the core-to-core transfer on this particular platform. Okay, so it really shows that we've trimmed away a lot of the overhead. And we're really hitting native limits on the particular platform. And then again, when we look out to the 5 nines, even at the 5 nines for Ring 0, we're still looking around about 200 nanoseconds, which so it's a tremendously flat curve as we go to the outliers. And again, it is worth just reminding that this is running with Chronicle Q, which helps control those outliers even further. Then similarly with across the different languages, so C++, Rust, and this time we're showing Java and also the JNI C++ POC, which is the yellow curve. So the first thing to mention here is with the Java, this is standard open source Java. We haven't shown Q Enterprise on this plot, but a big motivator for Q Enterprise is that we turn on additional performance optimizations, which again brings that curve much closer in line with the C++. But again, the yellow plot shows the capabilities that we can extract with JNI and C++. So down at the medians, the JNI overhead does cost us a little bit. So we are slightly higher than Java, but the benefits start to kick in above the 90th percentile, when we can really start to nail the outliers some more. Leveraging the C++ core for that particular use case. Okay, then just a quick slide for the Rust documentation. So the Rust offering for Chronicle Q is fully integrated with Rust docs. So you can see the link on the right-hand side, as well as a QR code. And the look and feel is, of course, familiar to anyone with Rust. It's all fully documented. And fully open as well, so you can browse that link straight after the webinar. So moving on to some of the other pieces of functionality that we are introducing over the near term. So historically, application stacks have needed best performance on single machine, and as Peter was mentioning, with Chronicle roughly 10 years old, this has tended to be the use case through the 2010s, the traditional financial trading application stacks on standalone hardware, and so really looking to maximize performance on the on standalone machines. So that's where Chronicle really grew up from, and that was our tuning focus in particular, was to get best performance on the standalone machines. What we're seeing increasingly is a growing trend to highly distributed, containerized, dynamic platforms, where exchanging messages easily across multiple machines is now really becoming the main priority, especially as people adopt much bigger cloud footprints for their application stacks. Having the agility and the speed to really grow out across available hardware and continue to deliver tremendous performance across those distributed hosts is where the dial is shifting. So we are adapting Chronicle Q to really cover that use case as well. And there are generally two approaches to doing this. You can either go with a sort of a centralized broker approach, or you can go with a proxy approach. We've taken something of a hybrid approach. So what we're doing here is we're leveraging the replication for the read path, and then a proxy for the write path. So going into a bit more detail in this diagram, we've got a fairly standard Chronicle Q primary secondary pair on the right hand side. So we've got writers or appenders on the primary. The queue is then being replicated through replication agents onto the secondary, and the secondary is there fully up to date with the primary, then a hot capability should we need to fail over. So using the same core mechanisms, we're now able to spread the appender onto n other hosts. Okay, so this is showing an example where the appender is now running on a third host. We can have any number of hosts, as I mentioned. So what we're using here is the same core replication mechanism is being used to bring the data onto the secondary machine. So each secondary machine has its own local copy of the queue that's being built up via replication. So the tailor uses that locally, so it's getting all of the benefits of the high performance local memory mapping. So the look and feel is very much the same as the traditional single host model, although we're now moving out into multi-host. And then similarly, the application, the appenders still communicate with the same look and feel of writing to queue. But what's happening under the covers is we're going over the network to a write agent or proxy that's sitting on the primary. If you remember, with queue, only the primary host can write into the queue at any one time. But this allows us to complete the loop. So we're using production hardened fabric essentially. So we've got the replication link going over to the secondaries, and then a lightweight TCP link back into the write proxy back into the primary, and then everything else still works as before. So the whole idea is you don't need to change your topology, your fabric. It all still works exactly as it worked before. What we're doing is we're adding the capability to write from multiple remote hosts. Time frame for this is Q1, Q2 next year to be fully production hardened. We do have a demo available today, so the proof of concept is available right now. Then continuing with expanding the messaging theme, high performance distributed replicated key value stores is again a very familiar recurring theme for what people want to do with managing state. So we have in the past Chronicle Map and Chronicle Map Enterprise for these use cases. But what we've tended to notice over the years where clients have been using those products is, although the look and feel is very much very much a key value store map, formalized map framework, the way the clients actually use that actually fits quite a narrow use case, which, if we target that, allows us to get tremendous step up in performance by leveraging Q. Okay, so what Chronicle Q back map is doing is it builds directly on the foundations of Chronicle Q to provide very high performance distributed state management. So it's using essentially the same kind of topology, the same kind of fabric as we're showing with the sequencer approach, but now it's being wrapped and exposed as a key value store. So it allows you to think in terms of a fully distributed key value store, fully coordinated writes from any host, full HADR support, decentralized key value store, but everything is built on Q. So you've got the speed first and foremost, and you've also got the resilience of the Q backbone, but then you can interface with it via as a key value store. Again, this is available today. And moving on to the next slide, again, it all feeds into the same model, which is both the QBack map and also the sequencer are really building out the foundations to allow us to support in a much more natural way, so very dynamic, high uptime environments. And again, this is absolutely in response to the use cases that we're seeing across the cloud infrastructure. People expect to be able to dynamically bring up environments, balance load intraday, and that's exactly where we're targeting with these changes. So what we're really looking to do is first of all allow us to have fully dynamic replication. So by that I mean you have your topology set up, you're fully trading, there's an event, whatever, you need to scale to respond to that event, and it should be the work of a moment to bring up multiple additional nodes to take the additional load, and to balance those, to integrate those nodes seamlessly into a live stack. So that's what we have with the fully dynamic replication. As part of that, we need fully flexible integration. So what we have with the changes to replication is really building on the core that we have today and lifting it up to the next level. And in particular, this is the integrating with Raft. So we've got formal integration with the Raft methodology, leader elections. And again, this is meant to be fully dynamic across the landscape. It's really the intent is to absorb a lot more of the management, the configuration of large scale distributed environments, and more being done automatically, because it's a much more seamless engagement with an application stack. And then coupled in with this is a trend to real no downtime environments. And so what I mean by that is we've seen 24/7 demand for a number of years, but typically what that translates to is almost 24/7. So there tends to be a little bit of a window where you can you have a bit of downtime, you can schedule upgrades, etc. But increasingly, and this is especially in the crypto spaces, when people say 24/7, they really mean 24/7. So this is what we refer to as hard 24/7, in the sense that there is zero downtime. So this means you've got live upgrades, you're bringing up instances on demand. Everything has to work seamlessly through time boundaries. And like I said, the big one there is the live upgrades. So that again is all folded into the same model. So this is a whole program of work which we're looking to release through next year. We don't have any hard timeline on that as things stand at the moment, but we're looking in the first half of next year for most, if not all, of these changes to be fully production hardened and available.